All right, we're going to take a look at the following claim. So say that we have the ring of all continuous functions from the reals to the reals, and we look at the subset I consisting of all functions that evaluate to 0 at x equals 0. Then this is an ideal of R, and moreover, it's a maximal ideal of R. Okay, so I think it helps to look pictorially at what's going on here. So what does this ring of continuous functions look like? Well, we can draw some continuous functions. Maybe we have some kind of cubic function down here, something that looks like that. We could also look at the constant map. So maybe we have some kind of constant map here. Maybe this is like f of x is equal to 3. Maybe we have some kind of sinusoidal function beneath the x-axis, so something like this. This is also a continuous function. So these are all elements of our ring. Now, what does the ideal look like? Well, this is all continuous functions that evaluate to 0 at 0. So a parabola y equals x squared. So this is f of x is equal to x squared. This is a member of I. Also, the linear map f is equal to x. This is also in our ideal. And also sine of x is in our ideal. So I'm going to try to draw this as best as I can. So this is also in our ideal, something like this. So all functions that evaluate to 0 at 0 are in I. Okay, so we can recall that addition and multiplication in this ring of continuous functions is defined pointwise. So taking f plus g, well, this actually defines a function that sends x to the sum f of x plus g of x. And similarly for multiplication, multiplication is defined pointwise. So f times g actually defines a function which sends x to f of x times g of x. And from this definition, it's not too hard to see that this set of functions I is actually an ideal, because if we have two functions in the subset that both evaluate to 0 at 0, so if f of x, or if we take f plus g of 0, and if f of x and g of x are both 0, well, the sum is going to be 0 at 0. So the sum is again going to be in our ideal, so it's closed under addition. And for multiplication, it's even better, because if we take f times g of 0, and if it turns out that one of these is in our ideal, so if, say, f of x, if this is 0, then we have 0 times g of 0, and it doesn't matter what g of 0 is, because anything times 0 is just 0. So a member of the ideal times any element of the ring is again in the ideal, and that's exactly the absorption property that ideals need to have. Okay, so it's pretty obvious that this is an ideal of the ring of continuous functions, and we wanted to show that this is a maximal ideal. So what exactly does it mean to be a maximal ideal? Well, it means that if we try to find some proper ideal which properly contains I and is a proper ideal of R, then that ideal has to be equal to I or the entire ring. So there is no proper ideal that properly contains I. Now, this is actually really hard to show directly here, but we can use kind of a nice trick here, or a nice property of maximal ideals. So in particular, we're going to remember a property about maximal ideals. So if we have an ideal of a ring, well, this is maximal if and only if the quotient of R by the ideal is a field. So if R mod I is a field, then the ideal is maximal and vice versa. So if we can exhibit some kind of quotient ring, quotient by this ideal, and show that it's a field, then we can conclude that the ideal is maximal. And we're going to start on this by first defining a map. So we want to find a homomorphism. And so we're going to define a map. And there's kind of a natural choice here. I'm going to call it phi 0, and this is just the evaluation map at x equals 0. So this map phi 0 is going to send a continuous function to a real number, and it's just going to send some function f to the result of evaluating f at 0. And okay, so the first question is this map that we've defined a homomorphism? This is something that we need to check. And so we can take a look and see if it preserves addition. So what is phi 0 of f plus g? Well, this is going to be equal to, it's going to evaluate the function f plus g at 0. So this is going to be f plus g evaluated at 0. But remember that addition is defined pointwise, so this is the same thing as f of 0 plus g of 0. Now, on the other hand, phi 0 of f plus phi 0 of g, well, this is going to send the function f to f of 0. So f of 0, and then this is just addition in the real numbers, so plus g of 0. And this is exactly the same thing as if we add the functions in the ring of continuous functions and then send them to their evaluations at 0. So phi 0 of f plus g, this is equal to phi 0 of f plus phi 0 of g. So we also want to show that it preserves multiplication. And so we're going to take a look at phi 0 of f times g. So this is going to be the result of evaluating the function f times g at 0. But f times g defines a function that just sends an input to f of that input times g of that input. So this is f of 0 times g of 0. And similarly, if we look at phi sub 0 of f times phi sub 0 of g, so evaluate first at 0 and then multiply. Well, this is just going to be f of 0 times g of 0, and this is exactly the same as if we multiply first and then send to the evaluation. So phi 0 of f times g is equal to phi sub 0 of f times phi sub 0 of g. Okay, so this evaluation map preserves the multiplication. Now our last question is, does it preserve the additive identity? So does it preserve 0? So what is 0 in the ring of continuous functions? Well, that's just the map sending any x to 0. So this is kind of the 0 element in the ring of continuous functions. It's just this constant map sending everything to 0. Well, the result of evaluating this at 0 is going to be 0. So phi sub 0 of the 0 map so phi sub 0 of the 0 map is just 0. So it does preserve the additive identity. So our conclusion is that phi sub 0 is a ring homomorphism. Okay, and our next question is, well, what exactly is the kernel of this homomorphism? So what is the kernel of phi 0? Well, if we kind of think about it for a second, so this is going to be all of the continuous functions that get mapped to 0 in the real numbers. So let's say that we have a function f. So let's say that we have a function f in the kernel of phi 0. So by definition, the kernel is everything that gets mapped to 0 in the codomain. So that implies that f evaluated at 0 is 0. And that tells us that f belongs to our ideal. So actually the kernel of phi 0 is a subset of our ideal. Now, on the other hand, if we have some function in our ideal, well, that tells us that f evaluated at 0 is 0. And that's exactly what we need for f to be in the kernel of this homomorphism because the kernel is everything that gets mapped to 0. So the ideal is a subset of the kernel, but we have inclusions in both directions. So the kernel is a subset of the ideal is a subset of the kernel. So these are actually the same. So this tells us that the kernel of phi 0 is equal to the ideal I. Okay, there's one more kind of observation that I want to make about this homomorphism. And in particular, we can show that it's surjective. So if we kind of think about this, and we can go back to our graph here. So to show that phi sub 0 is surjective, we need to exhibit a continuous function for any real number. And it's not really too hard to see. If we look at the y-axis here, we have kind of one copy of the real line. So this is the real line. And if we have some real number, so say that this is y sub 0, well, I can just construct the constant map. So the constant map here. So for any y sub 0, which is a real number, we can find a constant map which simply sends any real number x to y sub 0, and this function is continuous. So this means that our homomorphism phi 0 is surjective. So we'll make note of this down here. So for any y sub 0, we can find a continuous function which gets mapped to y sub 0. So the result of evaluating the constant map everywhere is y sub 0. So if we evaluate it at 0, then we get y0. And if we call this maybe c y sub 0, so evaluating this at 0 is equal to y0. And phi sub 0 of c y0, well, this is just equal to y sub 0. So the point is that phi sub 0 is surjective. So phi sub 0 is surjective. Now we can apply the first isomorphism theorem for rings. So the first isomorphism theorem tells us that if we have a ring homomorphism, then R mod the kernel, so R mod the kernel of phi 0 is isomorphic to the image. Maybe I should write it like this. So it's isomorphic to the image of R under the homomorphism. So we noted that the kernel of phi 0 is just the ideal, so all continuous functions that get mapped to 0. So in our case, this is just R mod I is isomorphic to the image of R. But what is the image of R? Well, it's the entire codomain because phi sub 0 is surjective. So we spent all that time showing that phi sub 0 is surjective. And what is the codomain of phi sub 0? Well, it's the real numbers. So R mod I is isomorphic to the real numbers. So our next observation is that the real numbers are a field. So R is a field, and fieldedness, so the property of being a field, is preserved by ring isomorphisms. So this tells us that R mod I is a field, and using the property of maximal ideals that we mentioned earlier, so a quotient ring is a field if and only if the ideal is maximal. So this tells us that because R mod I is a field, that I has to be maximal. So I is a maximal ideal. And that's exactly what we wanted to prove.